Okay, now here we have Otto cycles. Now I will be recording this example, first example for Otto cycle. So here in the questions I say an Otto cycle has a volume compression ratio of 9:1. Compression ratio sometimes is referring to as expansion ratio, but for Otto cycle the compression ratio and the expansion ratio are actually the same. So in this case here, when you refers to the PV and TS diagram, wherever they say expansion or compression, that means they are either referring to the volume ratio or the pressure ratio. So in this case, they are referring to the volume ratio. So usually volume ratio is taken as the V maximum over the V minimum. So in this case, when you refer to your PV diagram, okay, the V max is V1 or V4, and the V min is V2 or V3. So you can take either V1 over V2 or V4 over V3 as the compression ratio or the expansion ratio of 9:1, the volume ratio. Okay, and in the question they have given us the heat supply or the heat input as 500 kilojoules per kilogram. Now at the start of the compression, so heat supply or heat input. Now when they say heat supply or heat input, okay, so it needs to refer to 0.2 to 3. Basically it is best to refer to TS diagram. State 0.2 to state 0.3 shows that there is an increase in entropy, but that it is not 0.1 or 2, 0.1 to 2 or 0.3 to 4, because 0.1 to 2 and 0.3 to 4 is actually referring to isentropic processes, so they shouldn't have any heat transfer involved in those two processes, that is 1 to 2 and 3 to 4. Now 2 to 3 is your heat supply, where you have the increase in entropy, and 4 to 1, as you can see the arrow flows from 4 to 1, means it shows that there is a decrease in entropy, so that is the heat rejected. So for heat supply and heat rejected under constant volume process, it should be equals to CV multiplied by T3 minus T2 for the heat supply, and then CV T4 minus T1 for the heat rejected. Okay, how you got CVT? Then you have to refer back to your non-flow energy equation. Okay, so the heat supply is 500 kJ per kg. Now at the start of the compression process, then let us refer to PV diagram. So at the start of the compression process, so that is only 0.1 to 2 that is referring to a compression process, where 2 to 3 is a constant volume, 4 to 1 is also a constant volume. So you cannot be referring to 2 to 3 and 4 to 1 because both are constant volume process. So that is only 1 to 2. And 3 to 4 is an expansion, so you can't refer to 3 to 4 as for the compression process. So at the beginning of the compression process, the pressure and temperature is 100 kPa and the temperature is 40 degrees C. So that means it should be referring to our 0.1 here. Okay, both of these diagram, okay, it has been pre-drawn, so it is much easier for you to refer to the diagrams from here. Okay, but then usually the diagrams we will have to draw it out before we solve the problem. Okay, now and then they ask us to calculate the thermal efficiency, the maximum cycle temperature, the maximum pressure, the network output, and then draw the PV and TS diagram for the above cycle. So I've drawn the diagrams for you, both the PV and TS diagram. So remember, okay, constant volume process or Otto cycle or petrol engine cycle consists of two constant volume process and two isentropic processes. So it goes in clockwise direction, remember that. So here we use the same method as we have done for Carnot cycle, a tubular method. So where you have pressure, volume and temperature. The volume here we are using meter cube per kilogram, and then you have state 0.1, 2, at 3 and 4. So pressure at 0.1 they have given us that is 100 kPa, 100 kilopascal. 100 kilopascal is basically 1 bar, because one bar is actually 10 to the power of 5 Pascal. So and then the temperature is 313 Kelvin, that is given 40 degrees C at the beginning of the compression process. So 40 plus 273, you have 313. So from the point 1 itself, you can see P1 and T1 we have already known. Then we can straight away move to state point 1 to find out the volume V1 first. So you can use basically the ideal gas law. V1 equals to mRT1 over P1. So the M, the mass, is not given. The mass is not given, and it is unknown whether it's 1 kg or more. So basically we don't use this, okay? And then, or if you want to use this, we will have to assume that the mass is equals to 1 kg. If you don't take mass as 1 kg, then you can just ignore the mass. Find out the volume as in meter cube per kg. Find out the volume as in meter cube per kg if you don't want to assume mass as 1 kg. Okay? So you got a volume of 0.9 meter cube per kg. So basically, it's better for you not to consider 1 kg. So you get a volume of 0.9 meter cube per kg. Then you fill it up into the table. So that is 0.9. And we know that 0.1 and 0.4 is actually a constant volume process. So V1 would be equals to V4. Okay, V1 would be equals to V4. And then after that, we know that the question has given us a compression ratio of 9:1. That is V1 over V2. So that is also equals to V1. V1 is equals to 9 times V2. Okay? Or you can have V2 by taking V1 divided by 9. So that is equals to 0.1 meter cube per kg. So once you have got your V2, fill it into the table, 0.1. And 2 to 3, we know that the volume is the same also. It's a constant volume process. So you can fill up 0.1 for V3 as well. Then from state point 1 to 2, because now here we have to find out the rest of the properties, that is the pressure and temperature at point 2, and then the temperature and pressure at point 3, and then the temperature and pressure at point 4. So you can use the isentropic compression, the temperature volume relationship, or the pressure volume relationship. Okay, so you can use the pressure volume relationship because you have known both the volume, and also in the questions they have given us the volume ratio. V1 over V2 is actually 9/1. And then the gamma, that is the adiabatic index, is 1.4. Okay, that is 1.4. And then there is the relationship between the pressure and volume, so that is power of gamma. If you take temperature to volume, it should be power of gamma minus 1. And if you take temperature to pressure, it should be power of gamma minus 1 over gamma. So substitute your P1, V1, V2, and gamma. So you have your P2, that is 21.7 bar. So fill it up into the table under the pressure column. So you have 21.7 bar. Okay, so to the next. So since we have got the pressure for point 2, now it is easier for us to find the temperature at T2 by taking ideal gas law, or you can take the relationship between temperature and volume for the isentropic process also. Okay, for state point 2, so if I refer to a single point, then it should be using the ideal gas law. So we have the ideal gas law here. There's a mistake again. I have already considered the mass as 1 kg. So actually you don't have to consider mass of 1 kg because the volume given as already in meter cube per kg. Okay, so you found out that the temperature, the absolute temperature at point 2 is 755.83 Kelvin. So you got that is for your T2. So fill it up. Then based on the heat supply that is given in the question. Okay, we know that heat supply is equals to CV, that is a specific heat capacity at constant volume, and for A is 0.718. We got the T2 and then we will be able to find out T3 with a heat of 500 kilojoules per kg. So you got your T3, 1452.31. So you fill it up into the table. Then you move to point 3, that is to find out the pressure P3. So you can use the ideal gas law again. Now this time I have already ignored the mess. So you got a pressure P3 by substituting your specific gas constant 0.2871 times 10 to the power of 3, temperature, absolute temperature 1452.31, and the specific volume of 0.1. So you got P3 41.7 bar. Okay, then to point 4, state point 4. Okay, so you can find out your T4. $601.9. Okay, so actually you should refer to state point 3 to 4 first. Sorry, there's a slight mistake here. So isentropic expansion from 3 to 4. So you can use a pressure volume relationship again. So you can find out your P4. Actually, you have to find out P4 first. Okay, that was my mistake. And then after finding out P4, then only you can find T4. Okay, so you just swap the two workings. Okay, so you can find out P4, that is 1.92 bar. So you can fill it up. So the table is completed. Now you can start finding out your thermal efficiency. Okay, so you can use, okay, the given formula. There is one formula that is given earlier or has been proven, that is equals to 1 minus 1 over RV, that is the volume ratio power of gamma minus 1. You can use that formula to calculate the thermal efficiency actually straight away, or you can use this method also. Actually, both will give you the same answer. So in this one, you have to find out the heat rejected as well. So heat rejected is 207.4 kilojoules per kg. The heat rejected is also equal to CVT. 4 to 1 is a constant volume process. So basically, when you refer to non-flow energy equation, when you neglect the work done, you will have your heat is equal to the change of internal energy. And the change of internal energy is actually equals to the CV multiplied by the changes in temperature. Okay, so that is your network. Once you got your network, you can find out your thermal efficiency. That is 58.5%.